In this video, we will be discussing exponent basics. This will cover the rules of what an exponent is, as well as zero exponents and negative exponents. The first part of exponents is that we are going to have a base. So we'll call the base b for now. This is any number, any integer, any rational number is going to be our base. We are also going to have the exponent itself. I'm going to use the letter n to represent the exponent because of the fact that e is actually a numerical value, so we don't want to mess with that. We have base, we have our exponent. Now, what our exponent does is it tells us that we're going to multiply our base times itself n number of times. For example, b times b times b times b times b n times, okay? Let's take an example, 3 to the power of 4. This is the same thing as saying 3 times itself 4 times. In this case, 3 times 3 is 9, times 3 is 27, times 3 is 81. Okay? I'm going to keep going with my 3's here as my example, but these patterns will hold true for all bases. Okay? 3 to the power of 3 is the same thing as saying 3 times 3 times 3, which is the same thing as 27. 3 squared. All right? 3 squared, or 3 to the power of 2, is 3 times itself, which is 9. Now, I get 3 to the power of 1. Any number to the first power is just that number itself. And we often don't write the exponent purely because of the fact that it's understood to be a 1 if there's nothing else written there. Really quick before I move on, this 3 as an exponent is called cubed very often, and the 2 is often called a square or squared. So if you hear those terms, that's what it's referring to, an exponent of 2 for squared and an exponent of 3 for cubed. Now, I want to take a look at some patterns that we see in these exponents. 3 to the 4th, 3 cubed, 3 squared, and 3 to the 1st. Now, to get from one to the other, you'll notice I have 4 3's here. And all I did was essentially divided by 3 in 3 to the 4th to get down to 3 cubed. Again, if you see 81 here, 81 divided by 3 gives me 27, okay? So I am going to essentially divide by 3 or multiply by 1/3 to get to the next one each time I move on, okay? This helps us when I get to 3 to the power of 0. 3 is moving down one exponent, so I'm going to simply divide by 3, okay? 3 divided by 3 is 1. So 3 to the power of 0 is 1. Please note in your notes, any number, any base to the power of 0 is always going to be 1 because we follow this pattern of dividing the base from the previous exponent. Continuing on, we have 3 to the power of -1. So now we're going to work with some negative exponents. We'll look at some patterns here in a moment, but let's point out that we're going to keep doing this division by 3 because that's our base to continue on. So 1 divided by 3 is 1/3, right? 1 over 3 to the power of 1, 1/3. Okay? I'm going to either divide by 3 or multiply by 1/3. I'm going to multiply by 1/3 when I get down to my negatives. It makes it a little easier to visualize. And then I have 3 to the -2, or 3 a negative square. And I get 1/3 times 1/3. In other words, 1 over 3 times 3, which is the same thing as 1 over 3 squared, or 1/9. Okay? I want you to make a prediction on your paper. What do you think is going to happen when I get to 3 to the power of -3? I'll give you 3 seconds to think about that. right. If you said we would divide this by 3 or multiply by 1/3, then you were correct. So I have 1 over 9 times 1/3. 1 over 3 times 3 times 3, right? So I have 1 over 3 squared times 1/3, or divided by 3. In other words, 1 over 3 cubed. And I know from my previous example that 3 cubed is 1 over 27. In other words, anytime I have a negative exponent, I am going to move that base to the denominator. The exponent will become positive in the denominator. Let's clear that up a little bit here. B to the power of n. And I'm going to place a 1, or the reciprocal, in the numerator. Okay? A couple of quick examples. I have 8 to the power of -2. I could rewrite this both as 1 over 8 times 8. That's expanded form, sorry. Or simplified form, it would be 1 over 64. Another example could be 4 to the power of 0. Think back, what is anything to the power of 0? If you said 1, you are correct. Or 4 to the power of 1. If you said 4, you are correct. Anything to the power of 1 is going to be whatever it started as. Let's say I have 5 to the power of -4. This is going to be 1 over 5 times itself 4 times, or 1 over 5 to the positive 4th. Anytime we get up into exponents of 4 or higher, we start dealing with some pretty significant numbers. The only time I'm going to request that you actually calculate 5 to the power of 4, or any number, any base to the power of 4 or higher, is going to be when you are dealing with a base of 2 or 3. But otherwise, our bigger bases are going to become unreasonable when I get to powers of 4 or greater. Okay? And one last quick example. Let's go with x to the power of 7 over y to the power of -5. Okay? So y to the power of -5 is in the denominator. Let's rewrite that a little bit clearer. I'm going to write that a little bit better. X to the power of +7 over y to the power of -5. So x to the power of 7 can't be simplified any more than it is, and it's a power of 7, so I'm not going to expand that all the way out. It's going to stay in the top, in the numerator. But y to the power of -5, I have a negative exponent. So a negative exponent tells me that I'm going to move that exponent and base to the bottom of the fraction, but I'm already in the bottom of a fraction. So what I'm going to do is I'm actually going to move it to the top of the fraction now. I'm going to move it to the opposite side. So I'm going to write x to the power of 7 times y to the power of +5 once I move it. X and y are different bases, so we're going to just leave that as it is. And we have our final simplified form.